Hi everyone. This video is an introduction to the topic of vector fields found in section 16.1 of our text. The vectors in the figure below are air velocity vectors that indicate the wind speed and direction at points 10 meters above the surface elevation in the San Francisco Bay Area. And we see at a glance from the largest arrows in part A that the greatest wind speeds at that time occurred as the winds entered the bay across the Golden Gate Bridge. Part B, however, shows a very different wind pattern 12 hours earlier. Now, in these pictures, associated with every point in the air, we can imagine a wind velocity vector. So this is an example of a velocity vector field. Some other examples of velocity vector fields are illustrated in the pictures below as ocean currents or as flow past an airfoil. Now, another type of vector field called a force field associates a force vector with each point in a region. And an example is the gravitational force field we see in figure 3. Okay, so I've shown you some pictures, but what in the world is a vector field? Well, in general, a vector field is just a function whose domain is a set of points, either in R2 or R3, and whose range is a set of vectors. So, when we talk about vector fields, the picture is just a bunch of vectors, a bunch of arrows. We can think of these as representing airflow, as representing ocean currents, or some other type of force. But all of these are just examples of vector fields. So our vector fields, we're going to start with a set D, a set of points in R2 or even R3. And that vector field, again, is just a function that's going to take each point in D to a two-dimensional vector. And so our pictures of vector fields will just have a bunch of vectors, a bunch of arrows. So if E is a subset in R2 or R3, our vector field is going to take that point in E, that XY point, to a vector, an IJ in R2. Or we can start with a point in R3, an XYZ, and a vector field is going to map that point to a vector PQR in R3. Let's do some examples to see what we mean. Suppose a vector field is defined by f of xy equals I plus xj. Let's describe f by sketching some of the vectors. For me, the first thing to do is to switch notations. I don't know why, but I prefer the angled bracket notation to the ij notation. You do not have to do this. This is just my personal preference. So I'm going to rewrite my vector field I plus xj as in my angled brackets ix. And let's see where f maps a few points, starting with the point 1, 0. So notice that f of 1, 0 will be the vector 1, 1. So to sketch this, we'll start at the point 1, 0 and draw a vector that goes to the right 1 unit and up 1 unit. You see it here on the screen. Now, because of the nature of this particular vector field, we see that any point whose x component is 1 will also map to the vector 1, 1. So, for any point whose x component is 1, it will map to a vector that points to the right 1 unit and up 1 unit. Okay, what about another one? What about the point 0, 1? So, f takes the point 0, 1 to the vector 1, 0. So starting at the point 0, 1, we will draw a vector that moves to the right 1 unit, but doesn't move up or down at all. Notice that this vector field takes any point whose x-coordinate is 0 to the vector 1, 0. So let's sketch some more of those. For other points whose x-coordinate is 0, they will map to vectors who go to the right 1 unit, but don't go up or down at all. What about the point negative 1, 0? This vector field is going to map the point negative 1, 0 to the vector 1, negative 1. So starting at the point negative 1, 0, we'll draw a vector that goes to the right 1 and down 1. Notice this vector field sends any point whose x-coordinate is -1 to the vector 1, -1, so we can add some vectors accordingly. Okay, so here is a rough sketch of this vector field. Conceptually, again, you can think of this as showing us how wind is blowing in an area, how ocean currents are moving, or how some other force is taking place. So the best way to picture a vector field is to draw the arrow representing the vector f of xy, starting at the point xy. Now, of course, it's impossible to do this for all points xy, but we can gain a reasonable impression of our vector field f by doing it for a few representative points, as we see in the figure below. Let's do another example. A vector field on R2 is defined by f of xy is -yi plus xj. Let's describe f by sketching some of the vectors. As before, I'm going to begin by rewriting our vector in the angled bracket notation. So f is going to take the point xy to the vector -yx. Let's see where f maps a few points. What about the point 1, 0? So f is going to take the point 1, 0 to the vector 0, 1. So to sketch, starting at the point 1, 0, we will draw a vector that does not go left or right at all, but points straight up, has a vertical component of 1. Now, we can't cheat with our symmetry like we did on the first example, so let's just go through a few more points. F is going to take the point 0, 1 to the vector -1, 0. So starting at the point 0, 1, we will draw a vector that points to the left 1 unit, but has no vertical component, so doesn't go up or down at all. What about the point -1, 0? So f is going to map the point -1, 0 to the vector 0, -1. So starting at the point -1, 0, we will draw a vector with no left or right component, but that simply points straight down 1 unit. What about the point 0, -1? F will map the point 0, -1 to the vector 1, 0. So starting at the point 0, -1, we will draw a vector that points to the right 1 unit, but has no vertical component. Let's add a few more points to the mix. F will map the point 2, 2 to the vector -2, 2. So starting at the point 2, 2, we will draw a vector that points to the left 2 units and up 2 units. F will map the point 0, 3 to the vector -3, 0. So starting at the point 0, 3, we will draw a vector that points to the left 3 units but has no vertical component. F will take the point 3, 0 to the vector 0, 3. So starting at the point 3, 0, we will map a vector which points straight up 3 units. Here's my rough sketch of a few of these vectors. Now let's see one that was generated by a computer. It looks a little bit nicer, but that's okay. In general, because sketching all of these vectors by hand is tedious, we will normally actually use a computer to generate what these pictures look like. Now, if we imagine a fluid flowing steadily along a pipe, and we let v be the velocity vector at the point xyz, then v assigns a vector to each point in a certain domain E, the interior of the pipe, and so v would be an example of a vector field on R3 called a velocity field. You see a picture below in figure 5. Now the speed at any given point is indicated by the length of the arrow. And velocity fields occur in other areas of physics as well. For example, the vector field in example 2 could be used as the velocity field describing the counterclockwise rotation of a wheel. Alright, this is all for our introduction into vector fields. In our next video, we'll talk about tricks for matching vector fields with their plots and also about something called gradient fields. I'll see you then. Bye.